Hello students, today we are going to discuss NCERT section 9.5 to 9.5.1 and example 9.5 of ray optics and optical instruments. So this is the disclaimer. By the end of this lecture, you will be able to understand refraction at spherical surfaces and apply the fundamental equations for both curved and plane surfaces. We have discussed about the spherical mirrors in the reflection. Now in refraction, we have discussed the refraction through interface, that is plane interface. Okay, and also we have discussed the total internal reflection. Now we will discuss the refraction at spherical surfaces, like we have discussed reflection at spherical reflecting surfaces. Okay, now we are going to discuss spherical refracting surfaces. Okay, so means light is traveling from one medium to another medium, but the interface is spherical through which light is entering another medium. Okay, so now by the end of this lecture, you will be able to understand refraction at spherical surfaces and apply the fundamental equations for both curved and plane surfaces. Okay, so we will discuss about the curved surface and then we will do the special case of plane surfaces. Okay, now sign conventions and geometrical relationship we are going to discuss. Okay, that we have discussed in spherical reflecting surfaces, or in spherical mirrors we have discussed sign conventions. Okay, some geometrical relationships we have seen. Now similarly, we will see the geometric relationship and sign conventions for the spherical surface also, used in analyzing refraction through spherical interfaces. Okay, so index of topic that we are going to discuss is NCERT section 9.5 refraction at spherical surfaces and by lenses. 9.5.1 NCERT section refraction at spherical surface. And example 9.5. So let's start with refraction at spherical surfaces and by lenses. So what is spherical surface? Okay, so a curved surface that forms a part of sphere. What was spherical reflecting surface or spherical mirror that we have discussed? That was the also a part of a sphere. Okay, but we discussed that if the reflecting surface is curved outwards, then it is convex mirror. If the reflecting surface is curved inwards, then it is which mirror? Concave mirror. Okay, now we will discuss which type of curve represent which type of spherical surface. Okay, so it begins by defining the spherical surface, which is crucial for understanding how lenses work. Okay, now we will discuss similarly as two type of mirrors. We will discuss two type of spherical surfaces. One is convex, one is concave, explaining their shapes and optical significance. Okay, so a curved surface that forms part of a sphere. Okay, a surface that is a part of a sphere, or that forms, if we extend that surface, okay, that forms a part of a sphere, or we can say that surface is a part of a sphere, is called the spherical surface. Okay, so which type of spherical surface? So imagine a surface of a ball, it is curved outwards. Okay, so convex surface, a surface that curves outwards like a surface of a ball. If there is a glass ball, okay, so its surface is curved outwards and it is glass ball, and out in the surrounding medium is air and it is made of glass. So light is traveling from air to the glass. Since its surface is curved, so it behaves as spherical surface. Okay, so it behaves as spherical interface, and that surface is called the surface that is curved outwards. Outward means that is curved towards the medium from which light is coming. That is convex surface. Okay, so convex surfaces are crucial in optics because they can converge light rays, which is essential for focusing light in lenses. Okay, so after learning the spherical surface, we will learn about lens. So it is the basics to learn about lens, that how lenses are formed. To define lens, firstly we will discuss about the spherical surface. Second surface is concave. Okay, so you can a surface that curves inwards, like inside of a glass ball. Okay, so glass ball. Okay, so inside of a glass ball is representing the concave surface. Okay, so picture the inside of a ball, it curves inwards. So concave surfaces are also important because they diverge light. Okay, convex surfaces converge light, and concave refracting surfaces diverge light rays, which can be used in application like telescope. Okay, to spread light over a large area. We will discuss telescope and we will discuss about the concave surface. Okay, so a surface that curves inwards like a inside of a ball. Now, what is center of curvature? We have discussed about the center of curvature of a spherical mirror, of a convex mirror, of a concave mirror. Similarly, there is a center of curvature for spherical refracting surface. Okay, so center of actual sphere of which the spherical surface is a part. Okay, we have cut out the spherical surface from a whole sphere. There is a whole glass sphere. We have cut a small part, small portion from this glass sphere that we know that is surface, convex surface or concave surface. Okay, depending on the type of the shape from which we have cut out the surface. So the center of the actual sphere from which we have cut out the spherical surface, that the center of that sphere will be center of curvature. Okay, so this point is vital because it helps us understand how light will behave when it hits the surface. Okay, remember the center of curvature is always outside the lens for a convex surface and inside for a concave surface. Okay, so what is principal axis? We have discussed. So a line that is passing through center of curvature of the spherical surface is principal axis. Okay, in the case of mirrors, the light passing from the pole of a mirror, of a spherical mirror, and center of curvature, or we can say line joining the pole of a spherical mirror to the center of curvature and extended on both sides is principal axis. Okay, in the case of spherical refracting surfaces, okay, there is a midpoint of the spherical surface also like pole. We will connect this midpoint with the center of curvature of the spherical surface and we will extend it on both sides. That will be principal axis. Okay, so an imaginary lines passing through the center of curvature of the spherical surface. It's like the backbone of the lens, helping us predict the path of light rays as they pass through. Okay, so understanding the principal axis is the key to mastering ray diagram. Okay, we will determine how object will be placed at. Now we'll derive an expression with the help of based on the spherical refracting surfaces. Okay, we will take the object at principal axis and we will also take the image at principal axis. So it is very important geometrical property that we are going to use in spherical surfaces. So what is principal focus? Okay, so similar terms only we have discussed in the case of reflection. Now we'll discuss in the case of refraction. Okay, terms are similar. So what is principal focus? So the point on the principal axis where parallel rays converge or appear to diverge from a point. Okay, so point, okay, where after parallel rays coming along with the principal axis converge after refraction. In the case of reflection, we say the light rays converge after reflection from the mirror. In the case of refracting surfaces or spherical surfaces, we say the point on the principal axis where parallel rays converge after refraction through the spherical interface. For convex surface, or appear to diverge from a point, from that point for concave surfaces. Okay, so now what is next? Optical center. So this is the central point of the lens and it's important because it's point through which light passes without being refracted. Okay, when we are going to see the lenses, we are going to study the lens in our upcoming lecture. Okay, we will see what is optical center and why line passing through the optical center will pass undeflected. Okay, we have discussed that line passing through the center of curvature. For mirrors, line passing to center of curvature will retrace its path. Okay, but in the case of lenses, there is a midpoint or central point on the lens. Okay, the light ray through that central point will go undeflected. Okay, that is optical center, the center point of the lens. What is radius of curvature? Radius of the sphere of which the curved surface is a part. So we know that what is center of curvature. So the distance from the midpoint of the spherical surface to the center of curvature is known as radius of curvature. Okay, so this is the radius of the sphere from which the lens curved surface is a part. So from which that spherical surface is taken, that sphere. Okay, that sphere of which that spherical surface is a part. So radius of that sphere. So it's a measure of how curved the lens is or how curved the spherical surface is. A larger radius means a flatter surface. Okay, if the radius is very large of any spherical surface, that means that surface is somewhat flatter. Okay, for a plane surface, radius is infinite. So if radius is very large, it means surface is nearly flat. If radius is very small, it means surface is more curved. So what is focal length? The distance between the optical center and the principal focus. Okay, a shorter focal length means a stronger length. Stronger lens, or shorter focal length means stronger spherical surface. Okay, so we are discussing the spherical surfaces and lens side by side because lens are spherical concept of spherical surfaces are basic for or which lay the basis for lenses. Okay, so that's why distance between the optical center and principal focus. What is sign convention for lenses, or we can say spherical surfaces? Sign convention for spherical surfaces or lenses both are similar to mirror conventions but adapted for refraction. Okay, so remember, these conventions help us determine the direction and nature of the images formed by the lenses. Okay, so the formula we derive, any formula we derive, so we have to put the values according to sign conventions. Only then we will receive or we will get the accurate answer. Otherwise, we will get wrong answer. So object distance, so negative for real objects, and that is light incident from left. Okay, so if any spherical surface is there, if any lens is there, so light coming from left, that is the direction of incident light. So object is placed in front of the spherical surface or lens. Okay, so we are measuring for every distance from the pole or from the optical center in the cases of lenses. Okay, so we are measuring in the opposite direction of the incident light. That's why object distance for real object will also be taken as negative. Okay, so this means when light is incident from left, we consider the object distance as negative. This convention helps us maintain consistency in our calculation. So image distance represented by V, okay, it is positive for real images. Okay, in the case of mirrors, it is negative for real images because real images formed in front of the mirror. But in the case of lenses or in the case of spherical surfaces, real images formed on the other side of the lens or spherical surface. Why? Because refraction is going on, not reflection. So light is passing or entering into the another medium and forming image in the another medium. Okay, so that is real image. So real image in the case of lenses or spherical surface formed in the other side of the lens. So image distance is positive for real images. This occurs when light emerges to the right. Okay, it is important to note this because it tells us where the image will form relative to the lens. Okay, in the case of mirror, real images form in the front of the mirror, but in case of lenses or spherical surfaces, real image formed on the other side of lens or spherical surface. So what is focal length? Positive for converging lens, negative for diverging lens. What is converging lens? Okay, light rays coming parallel to any lens or spherical surface. After refraction, if the light rays will converge, then that lens or spherical surface will be converging. If the light rays will diverge, then that spherical surface or lens will be diverging. Okay, in the case of mirrors, concave mirror was converging mirror. Why? Because light rays falling parallel to the principal axis on this mirror, after reflecting, they converge at one point called focus. Okay, so that was converging, and convex mirror was diverging mirror. Okay, but here focal length positive for converging lens. Okay, so if light rays after refraction through the spherical surface will converge at one point, then focal length for that spherical surface will be positive. And if the light rays after refracting through the spherical surface are diverging, then focal length will be negative for that lens or spherical surface. Okay, so what is radius of curvature? We have discussed. So radius of curvature is positive if lens lies to the right of the surface. Okay, so this helps us understand the geometry of the lens and how it influences the path of the light. Okay, now refraction at spherical surface, the bending of light as it passes from one transparent medium to another through a curved surface. Okay, now bending of light is there, that is called a refraction, but till now we have discussed through plane interface. Okay, so bending of light when it passes from one medium to another, plane interface, like slab, it has interface, that is interface is the surface that is separating two media, air or glass, water or glass. Okay, in the case of slab, so that interface is plane, but now we are discussing about the curved interface. So bending of light as it passes from one transparent medium to another through a curved spherical boundary is called as refraction at spherical surface. Okay, so what is example? So the human eye, cornea and lens are also spherical surfaces. Okay, so you can see your shape of your cornea, that is outer part of the eye, is spherical. It is not plane. Okay, also it acts as spherical surface that refract the light to focus image into the retina. Also the lens present in your eye is also a convex lens. Okay, so it is a convex lens and both the surface of the lens are spherical. Okay, so the light is falling on cornea and then lens. Both are surfaces of both lens and cornea are spherical. Okay, so human eye is the example. Human eye, cornea and lens are also spherical surfaces that refract light to focus images onto the retina. Okay, the cornea and the lens of the eyes are spherical that refract light to focus image onto the retina. This is a great real world example of how refraction helps us to see clearly. Okay, so they are focusing or converging the light rays onto the retina so that sharp image will be formed on the retina and our brain will process it and we can see the outer world. This bending occurs because the speed of light changes as it enters a medium. Okay, we have discussed what is refraction, the bending of light when it enters another medium. Okay, so when it enters the denser medium, speed of light decreases, so it will bend towards the normal. When it enters a rarer medium, the speed of light increases. Okay, and light will bend away from the normal. Okay, so this bending occurs. Why this bending is occurring? Because of the speed of light is changing as it enters a medium with a different refractive index. Okay, if medium is denser, refractive index will be more. If medium is rarer, refractive index will be less, causing the light rays to change the direction. Okay, so when light enters a medium with a different refractive index, its speed changes, also its wavelength changes, but frequency remains same, causing the light rays to change the direction. This concept is fundamental in understanding how lenses can focus or disperse the light. This bending causes light rays to converge or diverge, creating real or virtual images. Okay, either light rays will converge, and if they are converging, then real image will be formed. If they are diverging, then we will extend them in the backward direction and virtual image will be formed. And that image, the point at which this virtual image is forming, that point, from that point we can say the rays after refracting appears to come from that point, but they are the rays after refracting through the lens or spherical surface are not actually meeting at that point. That's why it is called virtual image. So this is type of refracting surface. Okay, so what type of this refracting surface? This is a convex refracting surface. Okay, or we can generally say it spherical surface. Okay, so this is a spherical interface which is separating the two media. Okay, one medium is having refractive index n1, other medium has having refractive index n2. Okay, so object is placed at the principal axis. We take some assumptions while deriving for this spherical surface, by deriving the expression for this spherical surface. Okay, so object and image are point sized. The angle made by incident ray with the principal axis, refracted ray with the principal axis, incident and angle of incident and refraction are all angles are very small angles. Okay, these are the assumptions. Okay, aperture of this refracting surface is very small, means that effective diameter. Okay, so that we can assume this perpendicular from n, this perpendicular, so this is lying very close to m. Okay, these are some assumptions while deriving. So figure 9.15 is representing refraction at spherical surface separating two media. Okay, consider refraction at spherical surface between two transparent media. So media should be transparent so that light can travel through both the media of refractive index n1 and n2. Okay, so the slide. So we have considered this spherical surface. An infinitesimal part of a spherical surface can be regarded as planar. So if a large spherical surface is given, so very small part of that large spherical surface can be considered as planar surface. Okay, if very large spherical surface is there, like our earth, okay, it is very large spherical surface. Okay, it is nearly spherical. So its surface is spherical, but very small part on which we can see that is looking like, that seems like plane surface. Okay, but actually the surface of earth is, when astronauts see it from the space, it looks like spherical, but when we see it from ground, it looks like plane. So that is a small portion of that large spherical surface. Okay, similarly, a very small part of a spherical surface can be regarded as planar, and the same laws of refraction can be applied at every point on the surface. Okay, so normal at the point of incidence is perpendicular to the tangent, like we have discussed in the spherical mirrors. How we draw the normal on spherical mirror? We draw a tangent at some point where we have to draw the normal, and we draw the normal to that tangent, and that normal passes through the center of curvature of that mirror. Similar thing is for spherical surface. The point N, or any point at which we want to draw the normal, we will draw the tangent here. Then we will draw normal to that tangent, and this normal will pass through the center of curvature of the spherical surface. So that is a spherical surface. It is a part of sphere. If we will extend this and make a sphere, so this is the center of that sphere, and distance from this point M to C, this is the midpoint of the spherical surface M. So distance from M to C is radius of curvature. Okay, and we will draw the tangent and normal to that tangent, and that normal will pass through the center of curvature. That's how we draw the normal at any point on the spherical surface. So normal at the point of incidence is perpendicular to the tangent plane to the spherical surface. Okay, at that point, and therefore passes through the center of curvature. Okay, normal at each point on the spherical surface passes through the center of curvature. So if we draw normal at any point, it will pass through the center of curvature eventually. Okay, this geometric property allows us to extend Snell's law to curved interface. Okay, Snell's law is n to 1 refractive index of second medium with respect to first medium is equal to sine I by sine R. Okay, how we will determine the angle of incidence and angle of refraction? By drawing normal on plane surface. On plane surface we can draw normal, but on curved surface, how will determine the incidence angle and angle of reflection? By drawing the normal on the spherical surface. How we can draw the normal on the spherical surface? We have discussed. We will draw the tangent on that point to the spherical surface, and we will draw the normal to that surface. And we don't have to draw the tangent also. We will draw the normal that is passing to the center of curvature. So at that point, we will join that. We will make a line joining the point on the spherical surface and center of curvature. That will be the normal on that point. Okay, because normal always pass through the center of curvature. So geometry of formation of image I of an object O. So this is object, this is I image of this object. So how this image is formed? On the principal axis of a spherical surface with center of curvature C and radius of curvature R is given. So this is object. Now ray is incidenting on the spherical surface from this object O at this point. So we'll draw the normal at this point, which is passing through center of curvature. So angle between this incident ray and normal is angle of incidence. Now you can see this is N2 is denser medium, N1 is rarer medium. So this ray, incident ray, will bend towards the normal. So it will bend like that. So this is the angle between the refracted ray and normal is angle of refraction. Okay, so this ray, refracted ray, will meet the principal axis at one point, which is image. Okay, this is center of, this is U, object distance from the center of the spherical surface. This is V, image distance from this center of this spherical surface. Okay, the rays are incident from a medium of refractive index N1 to another of refractive index N2. So rays coming from object will refract at that point, and it will bend towards the normal and enters the second medium having refractive index N2. Okay, so this change in medium is what caused the bending of light, and we will explore further. So remember, the refractive index is a measure of how much the speed of light is reduced inside another medium. Okay, so why this bending of light is occurring? Due to the change of speed. So in denser medium, speed of light is decreasing. That's why it is bending towards the normal. So we take the aperture or lateral size of the surface to be small. So what is aperture? Is the effective diameter of this surface. That thing, that diameter. that is joining two ends of this spherical surface. That is effective diameter. That is not actual diameter. Okay, so we take the aperture of the surface to be small compared to other distances involved so that small angle approximation can be made. So we have assumed that angles made by this incident ray, refracted ray with the principal axis and angle of incidence and angle of refraction. Also, the angle made by this normal with the principal axis is small angles. Why? We have taken the small aperture. So this refraction is happening within a very, very small region. So angles are taken small. So light rays bends according to Snell law at each point. So I have already discussed that how light is bending at this point according to Snell's law. So geometry of formation of image I of an object O on the principal axis of spherical surface is given in this diagram. So for small angles, we can use the approximation tan theta approximately equal to theta. So if the angles are small, we use the approximation sin theta approximately equal to theta. Also tan theta approximately equal to theta for very small angles. That's why we have taken the small angle approximation so that we can derive the expression for this refraction at spherical surface. So Nm, this is Nm, will be taken to be nearly equal to the length of the perpendicular. So M is midpoint of the spherical surface and N is point of incidence. Okay, so we have drawn a normal from N to this principal axis. Since the aperture is small, so the this normal is meeting this principal axis at some point. So this point lies very close to M. So we can say Nm will be taken nearly equal to the length of the perpendicular. So Nm will be taken nearly equal to the perpendicular because aperture is small from the point N on the principal axis. Okay, therefore for small angles, we get tangent of angle NOM. So tan of angle this NOM will be taken as, so tan of this angle NOM will be perpendicular upon base. So what is perpendicular? NM, or we can say MN upon base. Base is MO or OM. So tangent of this NOM will be MN upon OM, and tangent of this NCM will be this angle C. NCM, this angle. Tangent of this angle will be perpendicular. What is perpendicular here? MN upon MC. Okay. So tangent of NIM. NIM. So what will be the tan NIM? So perpendicular upon base. Perpendicular is NM again, or MN. Base is MI in this triangle NIM. Base is MI. So we have found the tan of NOM angle, tan of NCM angle, or tan of NIM angle. Okay. Now for triangle NOC, this triangle, the angle of incidence I is an exterior angle. So for this triangle NOC, this incidence angle is exterior angle. So exterior angle is the sum of two interior angle on the opposite side. So this I will be the sum of this angle NOM and NCM. Okay, so this I angle will be, according to theorem, exterior angle will be equal to the sum of interior angles on the opposite side. So these interior angles NOM and NCM. So I will be equal to NOM plus NCM. Okay. Now I will be equal to, so we know that tan NOM was equal to MN upon OM. Okay. So tan theta is approximately equal to theta. That means NOM angle will be approximately equal to MN upon OM. So we can write MN upon OM. Similarly, tan of angle NCM is MN upon MC. So for small angles, we have taken the small angle approximation. So tan NCM will be approximately equal to NCM, which will be equal to Mn upon MC. Mark it as 9.13 equation. So angle of incidence will be equal to that. Now similarly for the angle of refraction, R will be equal to NCM. So this R will be equal to, now you can see, what is this? This is NCM, and this angle is, this is NCM minus NIM. NIM. Okay. So you can see this angle, this one, NCM. NCM will be the sum of two opposite interior angles. This is exterior. So NCM is the exterior angle for this triangle NIC. So this triangle NIC, NCM is the exterior angle. So it will be the sum of R and NIM. Okay. So NCM will be R plus NIM. And from that, R will be equal to NCM minus NIM. So R will be, what is NCM? Tan of NCM was Mn upon MC. So we are taking the approximation tan theta approximately equal to theta. So NCM will be approximately equal to Mn upon MC. Similarly for NIM, Mn upon Mi. So mark it as 9.14 equation. Now by Snell's law, what is Snell's law? Sin I upon sin R will be N21, which is equal to N2 upon N1. Okay, and after solving, we have discussed in the refraction chapter, this expression we have derived, N1 sin I equal to N2 sin R. Okay, or we can say sin I upon sin R equal to N2 upon N1, or we can say N21. Refractive index of second medium with respect to first medium, which is equal to N2, absolute refractive index of second medium upon absolute refractive index of first medium. What is absolute refractive index? That is the refractive index of a medium with respect to refractive index of air. Okay, or relative refractive index of one medium with respect to refractive index of another medium. So for small angles also, so tan theta approximately equal to theta, also sin theta approximately equal to theta. So we can say N1 or sin I, in the place of sin I we can write I only, equal to N2. In the place of sin R we can write sin only R, because I and R are small angles, we have assumed earlier. So sin theta approximately equal to theta. So therefore Snell's law can be written as N1I equal to N2R. So substituting the values of I and R from equation 9.13 and 9.14, we get N1. So what was I? We have, according to 9.13 equation, we have derived the relation for I, which is equal to Mn upon Om plus Mn plus MC. Mn upon MC, which is equal to N2R. So what is the expression for R according to equation NCERT equation 9.14? Mn upon MC minus Mn upon Mi. Now we will put the values according to the sign conventions. Firstly, we will simplify it. So dividing by Mn and rearranging, because Mn is all over in the numerator of all the terms. So we'll divide the whole term on the both sides with Mn. So Mn will be get cancelled out, will be cancelled out. So N1 upon Om plus N2. So how N2 came here? So we have rearranged this equation. So it will become N1 upon Om plus N1 upon MC equal to N2 upon MC minus N2 upon Mi. So N2 upon Mi we have brought in the left hand side, and N1 upon MC we have brought in the right hand side. So it will become N1 upon Om plus N2 upon Mi equal to N2 minus N1 upon MC. And this is equation 9.15. So this is a solving part. After solving and rearranging and dividing by Mn, we will come to that part. Here Om, Mi and MC represent magnitude of distances. So what is OM here? You can see object distance. What is MI here? Image distance. What is MC here? Radius of curvature. So what is the expression for refraction at spherical surface? It is the relation between object distance, image distance, radius of curvature, and refractive indices of the two media in the problem, in the diagram. Okay, of two media on the either side of the spherical interface. Okay, so we will put the values of OM, MI, and MC according to the sign convention. So applying Cartesian sign conventions, you can see OM is object distance. So this is real object. So U will be negative because we are measuring from M point, from the center of the spherical surface. Okay, and rays are coming from left to right. We are going from right to left. So OM will be minus U, object distance. Image distance. Now this image is real because rays after refraction are actually meeting the principal axis and making the image. So this image is real. But now we are taking image distance as positive. Why? In the case of reflection, image formed on the same size of the object, on the same side of the object, is called real image in the case of mirrors. But in case of spherical surface, image formed on the other side of the object, or we can say refracting surface, is called real image. Okay, because after refracting, light rays are entering another medium, and after converging, they are meeting at a same point or at a principal axis and forming a real image. So that's why image distance is positive here, MI. We are measuring in the distance of incident light. Also, radius of curvature will be positive, MC. We are measuring from M to C in the direction of incident light. So MC will be positive R, radius of curvature. Substituting these values in the 9.15 expression, so it will become N2 by V, and we are putting U as negative, so it will become minus N1 upon U, and R as positive, it will become N2 minus N1 upon R. Mark it as 9.16 equation. So this is the fundamental equation for refraction at spherical surface. So this is the final expression. Now, for concave spherical surface or for convex spherical surface, this is the generalized formula, is applicable for both type of surfaces. Okay, either object placed in rarer medium, either object placed in the denser medium, it is applicable for all type of cases. Only you have to apply the sign conventions while putting the values of V, U, and R for a particular surface. Okay, now this equation holds for any curved spherical surface. Okay, for concave, for convex, either object in denser medium, either object in rarer medium, it is applicable for all type of cases. Only you have to take care about the sign convention. So what are the physical significance of refraction at spherical surfaces? So this is the equation 9.16. So this equation gives us the relation between object and image distance in terms of refractive index of medium and radius of curvature of curved spherical surface. So it relates the object distance, image distance, radius of curvature, and refractive indices of two media. This formula helps us understand the behavior of light in lenses. Okay, we will discuss the lenses in our next lecture, in tomorrow's lecture. So this is the basis to learn the lenses. So what are lenses? They are any medium bound between two spherical surfaces is called lens. Okay, so we'll define the lens with the help of spherical surface concept. Okay, so this formula helps us understand the behavior of light in lenses, the human eye, and the other optical system. So valid for both concave and convex spherical surfaces. So when the radius of curvature approaches infinity, so what does that means? So what does that mean? That the radius of curvature approaches infinity. That means surface becomes flat, surface becomes plane. Okay, so that's why radius of curvature becomes infinity. The spherical surface effectively become a plane surface. So what are the special cases? So this is a special case. When the radius of curvature approaches infinity, the spherical surface effectively becomes a plane surface. So from the equation 9.16 we have derived. So n2 upon v minus n1 upon u equal to n2 minus n1 upon r. So put r as infinity for plane surface approximation. So if r is infinity, 1 upon infinity will be 0. So n2 upon v minus n1 upon u will be equal to 0. Okay, so it will become equal to 0. That means n2 upon v equal to n1 upon u, and after rearranging we will get v upon u equal to n2 upon n1. So this is a powerful result because it shows the direct relationship between the image and object distance and the refractive indices. Okay, if there is a plane refracting surface, then ratio of image distance to the ratio of object distance will be the ratio of refractive index, absolute refractive index of second medium with respect to first medium. Okay, so example 9.5, light from a point source in air falls on a spherical glass surface. N is given 1.5 and radius of curvature. So light falls from a point source that is placed in air. That means n1 here is air, that is 1, n1 equal to 1, and n2 here is n, which is 1.5 for spherical glass surface. Object is placed in rarer medium and radius of curvature is given 20 centimeter. The distance of light source from the glass surface is 100 centimeter. At what position the image is formed? Okay, so u is given 100 centimeter. So object is real. That means u will be taken as negative. Okay, also radius of curvature 20 centimeter. It is also taken as positive, and image distance will be found. So let's see the solution. What is given in the question? So object distance u will be minus 100 centimeters, negative as object is in air to the left side. Okay, and it is placed in the front of the spherical glass surface. Radius of curvature will be taken 20 centimeter, positive as center is to the right of the surface. Okay, and it is also not given that which type of spherical surface is there. So we'll assume it as convex. So radius of curvature r equal to 20 centimeter. So refractive index of air n1 is equal to 1 because object is placed in air, and the refractive index of glass n2 is 1.5. Now we will put all the values in the expression we have derived for spherical surface. So applying the spherical surface formula, that is n2 upon v minus n1 upon u, which is equal to n2 minus n1 upon r, according to equation 9.16. Okay, so according to sign convention we will put the values. So substituting the values, n2 upon v minus n1 upon u, which is equal to n2 minus n1 upon r. So put the value of n2, which is 1.5, and put the values of n1, which is 1, u minus 100, and r equal to positive 20 centimeter. Now solve it for v. So 1.5 upon v minus plus by 1 by 100, 1.5 minus 1, which is 0.5 upon 20. So after solving it, so 1.5 upon v plus 1 by 100 equal to 0.5 upon 20. So 1.5 upon v, which is equal to 0.5 upon 20 minus 1 by 100, which is, after further solving it, taking LCM, it will become 0.025 minus 0.01. So 1 by 100 is 0.01 and 0.5 upon 20 is 0.025. So after subtracting, it will become 0.015. So 1.5 upon v, which is equal to 0.015. So v will be equal to 1.5 upon 0.015, which is 100 centimeter. So v is came out to be positive 100 centimeter. That means image formed on the other side of the object or refracting surface. The image is formed at distance 100 centimeter from the glass surface in the direction of incident light. Okay. Now, summary: refraction at spherical surface occurs when light passes from one medium to another through a curved surface. The fundamental equation for spherical surface refraction is n2 upon v minus n1 upon u, which is equal to n2 minus n1 upon r, which is applicable for convex as well as concave surface, as well as object placed in rarer or denser medium. Only you have to take care about the sign convention. When r approaches to infinity, spherical surface effectively becomes the plane surface. The equation simplifies to v upon u equal to n2 upon n1. Geometric relationship and Snell's law are used to derive the spherical relation refraction equation. The equations are valid for both converging and diverging surfaces. What is converging surface for spherical surface? That is convex surface. And diverging surface in the case of spherical surfaces, refracting surfaces. Diverging surfaces are concave surfaces. Okay, it also depends on the medium in which object is placed. Under paraxial conditions. What are paraxial conditions? That light rays that we are considering are very close to the principal axis, or we are considering very small part of the spherical surface which is almost flat and aperture is small. So there are some practice questions. If a spherical surface has a radius of curvature r equal to 20 centimeters separating air n1 equal to 1 from glass n2 equal to 1.5, where will the object placed 30 centimeter from the surface form its image? Next, for a plane refracting surface r equal to infinity separating two media with n1 equal to 1 and 2 equal to 1.33, if an object is placed 10 centimeter from the surface, where will be its image form? What is the focal length of spherical surface with r equal to 15 centimeters separating air and n1 equal to 1 from glass and 2 equal to 1.5? If an object is placed 40 centimeter in front of spherical refracting surface of r equal to 25 centimeter, air to water, n2 equal to 1.33. So n2 is the refractive index of water, which is 1.33. Calculate the image distance. Okay. For a spherical surface with r radius of curvature 30 centimeters separating two media n1 equal to 1.2 and n2 equal to 1.6. Find the image distance if an object is placed 50 centimeters from the surface. So thank you. This is all about today's lecture, refraction through spherical surfaces. Okay. So I hope you enjoyed the session and understood it well.